the last talk of this mini conference, Lucas Pannier, who is going to talk about effective proof of the p-curvature conjecture for order 1 linear differential equation. So, Lucas?
Yes, thank you for the introduction. Yes, can you hear me?
Yeah, we hear you. You can start.
Hello? Okay, so great. Yes. Okay. Thank you for the introduction, and thank you for inviting me and organizing this nice conference. So indeed, I will talk about an ongoing joint work with Florian Fürnsinn, whom we've heard earlier today. So let me just start by stating a few definitions about power theories. So we are interested in some properties that can be satisfied by power theories. Namely, the first one is power theories can be algebraic. This is if it satisfies polynomial equation with integer here coefficient, but polynomial in x coefficient. And we will say in this case that the power series is algebraic over Q of x. And an example of that is this root of a polynomial, which we can develop as a power series, and it satisfies this polynomial equation. Okay, another properties with which we have talked about is that the power series can satisfy a differential equation, and in this case we will say that y is definite if it satisfies such an equation. And an example is the exponential of a polynomial. It satisfies this kind of equation. And so these two properties are actually linked by Abel's theorem, which dates back to 200 years ago almost, which states that all algebraic series are definite. And however, coming back to my two examples, we see that these algebraic series satisfied a first order differential equation. However, it is not true that the converse holds, because this definite power series is not algebraic, as can be proved, for instance, by Eisenstein's theorem that was stated earlier. So the natural question arising is, can we decide what definite power series are algebraic? Because we know that some are, but not all of them. So everything I'm saying is about here power series, but we can generalize to Laurent series and even Puiseux series. Okay, so the question was actually asked by Abel already. If we consider a power series U algebraic over Q of x, so this is what this bar means here. Can we decide if the non-zero solutions of the differential equation y prime equals u times y are algebraic? The first remark on this problem is that this differential equation is satisfied by a very specific function, which is the exponential of the integral of u. And so we are wondering when this expression is algebraic. So two examples. If u is equal to 1 over the square root of x, then the solution y is not algebraic. But if u is equal to this rational function, then y will be algebraic. So we see that the answer to Abel's problem is non-trivial. And Fuchs actually stated a more general problem that for nth order linear differential equation, can we decide if all solutions of L times y equals 0 are algebraic? So for order 2 differential equations, for instance, this first equation has a transcendental solution, which is a logarithm, whereas this second differential equation has only algebraic solutions over Q of x. The Abel's problem has been answered by Risch and Davenport, and independently by Baldassari and Twork. And this work led to what is known as Risch algorithm to decide when the solutions of such a first-order differential equation are algebraic. And Fuchs' problem has also been answered in 1980 by Singer, whose work relied on Risch algorithm. However, here we will try to have a local global approach, so a different arithmetic approach. So let us consider a nth order linear differential operator, and we want to reduce it modulo p. And so that's what we will do by considering the reduction modulo p of all polynomial coefficients of the differential operator. And we will call this new differential operator LP, with coefficients in fp of x. And as was stated a bit earlier, Grothendieck stated in the 1960s, I believe, conjecture, which is just a local global statement, saying that all solutions of the differential equation in characteristic 0 are algebraic over Q of x if and only if the reduction modulo p of the equation has a basis of algebraic solutions for almost all prime numbers. One can wonder if having a basis of algebraic solutions over fp of x is really a property that is easily checked compared to checking it in characteristic 0. And so this is where the p-curvature intervenes. So I will not define it very precisely for any other differential equation, but it was defined before in Rosa-Install, for instance. So to LP, we can attach an fp of x linear map that we call the p-curvature. But what we will be really interested in is knowing when this p-curvature vanishes. So there is Cartier's lemma that allows us to check So there is Cartier's lemma, which states that the p-curvature vanishes if and only if LP of y equals 0 has a basis of algebraic solution. So we can restate Grothendieck's conjecture as Grothendieck's p-curvature conjecture. So all solutions of the differential equation are algebraic over Q of x if and only if almost all p-curvatures vanish. So this conjecture has been studied by a lot of people, and it has improved in many different cases. Here are some of them. And the one we will be interested in is mainly the first, the order 1 case. So order 1 with a rational coefficient has been proved by Honda in 1974, and then his result has been generalized by the Chodnovsky in 1985 to any first order differential equation with algebraic coefficients. What is the most interesting in this proof is that the tools used allows to make an effective statement. So I will explain in a few minutes what we call an effective statement here. But first, let us observe that when a solution is not algebraic, so this is an observation, this is not a theorem, but when a solution of a differential equation is not algebraic, we observe very quickly that some p-curvatures are non-zero. So for instance, for this first order differential equation, the 2 curvature is non-zero, and the 3 curvature is also non-zero. So this is a Honda's theorem, as I was saying, that the p-curvature conjecture holds for equations of order 1 with rational coefficients over the rational numbers. And as you can see, this is not a decision procedure. If you recall Abel's problem and Fuchs' problem, they asked whether we could have a decision procedure. And here we would need, in the p-curvature conjecture, to check infinitely many conditions, that is the vanishing of infinitely many quantities that are the p-curvatures. So what we would like to do is to state an effective version of this conjecture that is find that finitely many p-curvatures vanish to conclude on the algebraicity in characteristic 0. So first, let me develop a bit on what Honda did to prove his theorem. So I will try to give you an insight on why Honda's theorem is true by just doing a few computations in characteristic 0 first, and then in characteristic p, in positive characteristic. So if we consider this kind of first order differential equation, well, we know that the solution is the exponential of the integral of this coefficient a over b. So we want to, we can express a over b as a rational fraction. And so here is a polynomial part plus a polar part. And we will see that we can actually simplify this general case. So if we compute the solution of the differential equation with a over b equals x, we see that we obtain here an exponential of a polynomial, and this is not algebraic. And I hope that you trust me if I tell you that more generally, if the degree of a is greater than the degree of b, that is, if we have a polynomial part in our coefficient, then the solution y will not be algebraic. And so we can reduce it to 0 and consider only a over b to be a sum of some polar part. And we can do the same kind of computations with a over b equal minus 1 over x squared, for instance, and we obtain a solution which is a rational function and is again not algebraic. And more generally, we can see that if b has a double root, then y is not algebraic. So we can consider that a over b will only have first order poles. So we're actually interested in the statement of the conjecture. We're actually interested in differential equations over q of x that has this shape. A over b is a sum of some residue over x minus a pole. So what we have proved, if I recall correctly, is that the degree of a is smaller than the degree of b, and b is square free if we assume that y prime equals a over b times y has only algebraic solutions. Okay, but this is not an if and only if, as is shown by this example. If I take a over b to be 1 over x squared plus 1, we can express it as this partial fraction decomposition, and the solution exponential of arctangent is not algebraic. So the actual if and only if condition that we need is the following. We know that y will always have this shape with, so I did not state it before, but here beta i's are the roots of b, so they lie in the splitting field of b, and so the alpha i's also lie a priori in the splitting field of b, so they are algebraic numbers, and this solution y is algebraic if and only if all residues alpha I are rational. That is, if we put this expression to the appropriate power, we will obtain a polynomial. Okay, so now what happens in fp over fp of x in positive characteristic? Well, first recall that we had Cartier's lemma that allowed us to not check directly algebraicity, but to compute p-curvatures and then to conclude on algebraicity. And it happens that we have a theorem of Jacobson that gives a formula, a closed form formula for p-curvatures of first order differential equations. So if u is a rational function over fp, then the p-curvature of this differential equation is the p minus 1 derivative of u plus the p's power of u. This is a very specific to first order differential equations, as there does not exist a closed formula for higher order. And from this statement, we can derive many things with actually the same computations as we did in the characteristic 0 case. That is, if we know that if the p-curvature vanishes, well, we can compute this quantity for a general u, and we see that the only expression that you can have is this expression with this term alpha I and beta I algebraic over fp. And conversely, if you have this shape, then we can compute its p-curvature, and we see that it has this expression. So it is a sum of p-curvatures of alpha over x minus beta. And we know that this expression actually vanishes if and only if each of its terms vanishes. That is, if each alpha I to the p is equal to alpha I, and this condition means that alpha I is in Fp. So there is a little footnote because this is only true if p does not divide the difference of two roots. So this is if we were in characteristic 0, so this should not be here because we are in characteristic p. However, this only excludes finitely many primes, so we should not worry about this statement. So now we have seen that in characteristic 0, the solution was algebraic if and only if the residues were rational numbers. And here in positive characteristic, the condition is that alpha should be, the residues should be in Fp. And so we have reduced Honda theorem to proving that for a single alpha algebraic over Q, it is rational if and only if all modulo almost all primes, it lies in Fp. What we call here alpha mod P is a root of the reduction modulo P of the minimal polynomial of alpha. So in practice, in what's following, we will only consider all roots of a polynomial at a time and not a single root, but this won't be a problem. So this statement, this local global statement was actually known by Honda. It is called a Kronecker theorem, and it's a polynomial statement is that almost all, if we consider a polynomial R irreducible, then if this polynomial has a root in Fp for almost all prime numbers, then it has a root in Q and it is linear. So it was first stated by Kronecker in 1880 and then proved by Chebotarev in 1926 with a high-level number theoretic theorem. But there is actually another proof by the Chudnovsky in their 1985 article that we mentioned earlier. And I will talk about that later because this is what allowed us to obtain effective statements. So if we recall Honda theorem, and we recall that we have reduced Honda theorem to Kronecker theorem, and both theorems are equivalent, well, this consists of proof because we know that Kronecker theorem is true. And this was actually Honda's proof. And we can state Kronecker theorem in another way for a non-irreducible polynomial by replacing that the polynomial R has a root by the statement that the polynomial R should split completely. And if we come back to what we said on the last slide, well, we can take R to be a polynomial annihilating the residues of the rational fraction A over B. And this will, Kronecker theorem will apply to prove Honda theorem. So, what did the Chudnovsky do? They proved an effective version of Kronecker theorem. So if we consider R a polynomial with the leading coefficient delta, then there exists an integer sigma such that R splits completely over the rational numbers if and only if R mod P splits completely over Fp for all primes P that satisfy two conditions. They are not dividing delta and they are at most sigma. So this yields a finite number of primes. So this is what we call an effective statement because we only need to check finitely many conditions locally to conclude globally that R splits in Q of X, in Q of W, sorry. However, the Chudnovsky did not give a value for this sigma. And so this is our contribution with Florian Fürnzin. So we need to introduce two more parameters, this T depending on delta, and B, which is an upper bound on the modulus of all roots of R. And we state explicit values of sigma depending on two explicit parameters M and N. So this is what we hoped for. This is an effective statement of Kronecker theorem with an explicit bound sigma. This theorem was proved using Pannier approximation, which is a very effective tool, and this is what allowed us to explicit the value of this sigma. And before explaining what is a Pannier approximant, let me just state that we have a criterion from this statement, which is actually quite easy to see. That is, if for a single prime p satisfying that it is smaller than sigma and it does not divide delta, we have that R mod p does not split completely, then we can conclude immediately that R does not split completely in Q. Okay. So what is a Pannier approximation? Well, it is a it comes from a problem, actually. The problem is given some power series and two parameters. Can we find polynomials such that the degrees of this polynomial are bounded by the parameter n, and the linear combinations of the power series with polynomials have a prescribed order, at least. So an order S equal to the second parameter. So this is actually a linear algebra problem because we can consider the coefficients of the PIs to be indeterminates. And so we have R times n plus 1 such indeterminates. And if we want all S first coefficients to vanish, this gives S linear homogeneous equations. And so the value S equals R times n plus 1 minus 1 should always hold. So we can always find polynomials PIs satisfying these conditions with this value of S. So this method of Pannier approximants were introduced by Hermite in 1873, which allowed him actually to prove that E is transcendental in its original proof. And it was then continued by many people, including Mahler, whose work is crucial to the proof of the Chernovsky. So what's the link between Pannier approximation and algebraicity of some functions? Well, if we take the very specific case when the power series Fi's are powers of the same power series F, well, F will be algebraic if and only if the remainder of the Pannier approximation vanishes for large enough values of n and r. And so this is what we will use here. Let me explain the proof of the Chernovsky. Let me explain Chernovsky's proof of Kronecker theorem. If we assume that R has a root that is non-rational, that is, we assume that R does not split completely in Q, we can write L to be equal to Q of alpha. And then we know, thanks to Mahler, explicit Pannier approximants Pi of Z with bounded degree to this function 1 minus z to the alpha. So as we have assumed that alpha is not rational, we know that this 1 minus z to the alpha is algebraic if and only if alpha is rational. And so here we know it is transcendental. So we should not be able to obtain 0 on the right-hand side here for any value of n and any value of m, which is the number of functions we approximate. And in fact, we know here not only explicit expressions of the PI, but we also know that so sigma is this value from the linear system that I explained earlier, and we have an explicit expression of G, which is this rational coefficient, which is in particular non-zero. What the Chernovsky used then is a classical inequality, which is quite trivial. So let me just state that the denominator of an algebraic number is the smallest integer, such that this denominator times the algebraic number becomes an algebraic integer. So if we now consider gamma in L to be non-zero, should have said that, gamma is non-zero, and we multiply the norm of gamma by the appropriate power of its denominator, then this should be greater than 1 in absolute value. And what the Chernovsky do in their proof is to construct a contradiction from this contradiction of this inequality. So they construct a sequence of algebraic numbers gamma and n. All are non-zero, and m and n are the two parameters of our Pannier approximation, such that this left-hand side of the inequality has a nice asymptotic equivalent, which is some function of m to the power n times some function of m, where x of m has the particularity that it goes to 0 as m goes to infinity. And so now, for large enough m, that is for whenever x of m will be smaller than 1 in modulus, and for large enough n, we can have that this whole expression becomes 0, yielding a contradiction between this inequality that holds in any number field and this inequality. Hence, we can conclude that alpha should be in Q. So one might wonder that where have we used that R mod P should not split, that is, that R mod P should split in FP, that is, where have we used that alpha mod P should be in FP? Well, the answer is in the denominator here. To obtain such asymptotic equivalence, we really need to have arithmetic estimate of these denominators. Let me state it a bit more clearly. We have this lemma that allows us to know what is the denominator of such a binomial coefficient k alpha plus L choose R, where alpha is an algebraic number. So if we consider prime P that does not divide alpha and and a prime ideal above P, then we know that if alpha mod P lies in Fp, then P does not divide this denominator. However, if alpha mod P is not in Fp and P divides this denominator, then we know that P is smaller than R. So what tells this lemma is that the denominator of this binomial coefficient consists of primes dividing the denominator of alpha and primes smaller than R, such that alpha mod P is not in Fp. So if we assume that alpha mod P is in Fp for almost all prime, well, this binomial coefficient will have only finitely many primes in the denominator, whatever parameters we choose. And so why is it a key lemma? It's because these binomial coefficients appear in the Pannier approximation that Chernovsky put with R smaller than sigma. And so this is why this sigma is the bound on the number of primes we need to check. It is because this is it's really because this is all the primes that can appear in the binomial coefficients. So to conclude this proof, so I presented you the Chernovsky proof, but we proved something more precise, for which we needed explicit error terms so that we could write inequalities instead of asymptotic equivalence. And with these two tools, well, we could conclude on our theorem. And let me now state another theorem. I told you before that to make the link between Honda's theorem and Kronecker's theorem, we needed a polynomial that annihilates all the residues of a rational function. Well, if we assume that A and B are two polynomial and B is square free, then we can construct a polynomial, which is exactly this one, with residues exactly with the roots. The residues of the rational function A over B. So this is known as Rothstein-Trager's polynomial. So we can state as a corollary an effective version of Honda's theorem. If we take two if we take two polynomial A and B and compute their Rothstein-Trager polynomial, to which we apply the previous result. So with delta, the leading coefficient, which is actually the resultant of B and minus B prime, the same T as before, the same B as before, the same values of M, N, and sigma. Then we can state that all solutions of Y prime equals A over B times Y are algebraic if and only if the p-curvatures of the differential equation vanish for all primes P that do not divide delta and that are at most equal to sigma. So we have what we hoped for, an effective version of Honda's theorem. This yields actually an algorithm that we can implement, which takes as input the two polynomials of the coefficient of our differential equation and output the nature, algebraic or transcendental, of the solution of the differential equation. Well, the algorithm is not very complicated. From now on, we need to compute the Rothstein-Trager polynomials and the different parameters associated to it. And then we can compute our value of sigma and then compute all p-curvatures until we find one that is non-zero. Then we can return transcendental immediately. And if we have tested that all p-curvatures vanish for p up to sigma and that do not divide this value, this leading coefficient delta, well, we can return that the solution is algebraic. We have a complexity estimate of this algorithm. Here, computing the Rothstein-Trager polynomial is done in O tilde of d squared bit operation, where O tilde hides logarithmic factors in D. And here, we have an algorithm to compute also p-curvatures thanks to Boston and Schost. Also, we can express sigma in terms of delta and B. This is approximately B times delta to the 6, so we can express our complexity in this way. However, what we're doing in this algorithm is we're computing a polynomial and we want to check if all its roots are rational. So one may wonder, why aren't we just factoring this polynomial? Well, we can do that. This yields indeed a second algorithm solving Honda's problem. So the algorithm takes the same input, gives the same output. It starts by computing the Rothstein-Trager resultant, then factor it, and then it splits. If R splits completely, we can return algebraic and then return transcendental. So we have the same complexity here, but what about factoring? So the best, to my knowledge, the best algorithm for factorization is due to Van Hooij and Novosin, which allow to factor univariate polynomial of degree d over the integers with coefficients bounded by some a. In this complexity, and in our case, the logarithm of a is approximately d, so we can say that this is in O tilde of d to the 6. A few algorithmic questions. The first one is, how can we compute p-curvatures? So I said that there is an algorithm due to Boston and Schost in 2009. It actually allows to compute first p-curvatures for first-order differential equations. Yes, and so we can use this algorithm to compute all p-curvatures up to some bound n. And there exists another algorithm due to Pages, which allows to compute p-curvatures for any linear differential equation, I mean for any order, and up to a certain bound. That is, the algorithm does not compute just one p-curvature, but all p-curvatures up to a bound, which is what we want to do. This algorithm of Pages is a bit less efficient than the one of Boston and Schost in the case of order 1. However, that is the one we used in our tests for the moment. So I have here, I can present to you 3 tests, so very basic tests. using the first algorithm that I presented. So if we take this A and this B, which is a very trivial case because A is equal to B prime, so we know that the output will be algebraic. The sigma, the bound on the primes to check, is 3000 approximately, and we can compute all P curvatures in a few seconds only. However, if we take another example, which is the first non-trivial example we checked, that is, this is an example of A of degree 1, B of degree 2, which is not, which outputs algebraic, but which is not just a derivative over the polynomial. And we see that this sigma is quite large, and in practice, this takes very long to check for the moment that all P curvatures vanish. But the advantage of our algorithm is that we can check for any kind of polynomial. So if we take this A and this B, well, the algorithm will return transcendental, and even though this sigma is very large, well, the phi curvature is already non-zero, so our algorithm will return very quickly the answer to our question. For the moment, of course, the first algorithm does not compete with the second algorithm because factorization has been studied a lot and implemented and optimized, which is not at all the case of the first algorithm I presented using P curvatures. And last, I would like to make a bit of a link with another problem in number theory. So I said before that I knew two proofs of Kronecker theorem, one due to the Chodnovsky, which I presented to you in the slides, and the second due to Chebotarev using a high-level number theoretic statement, which is a Chebotarev's density theorem. And there actually exist effective versions of this theorem. So I will not state very precise things, but I will try to highlight a link. So there is a fact. So if we consider a polynomial R with integer coefficients, splitting field L, and degree of the splitting field over Q, small l, well, we can relate the factorization pattern of R modulo a prime of Z to a factorization pattern of the prime in the splitting field of R. An example is this polynomial. So if we ignore the prime P equals 2, which is singular, which is ramified actually, then we know that this polynomial factors if and only if P is congruent to 1 mod 4. And it happens that the splitting field of this polynomial is Q of I, and with an integer ring Z of I, the gross integers. And we know that any prime congruent to 1 mod 4 can be written as a sum of two squares, and this allows us to factor P in over the Gauss integers. So from this statement, we can actually find a new problem because we wanted to find when R mod P does not split. So our new problem is to find when P does not split in some splitting field of a polynomial. So we want to obtain an upper bound on the first prime P that does not split in L. This is really equivalent to our previous problem. And so I said that there exist effective versions of Chebotarev's theorem. I will not state them all. There are a lot of different results in different directions, but I will just state one, which uses, it says essentially that there exists a prime P that it does not ramify, does not split completely in L, and that is smaller than some bound here, depending on two parameters, one being the degree of the extension of the splitting field, and the other being the discriminant of the splitting field. And just one remark is that this degree of L is not equal to the degree of our polynomial in general, and this discriminant of L is not equal to the delta, which is the leading coefficient of our polynomial in general. So we do not use the same parameters in the two problems. So let me end on perspectives for this work. We have, for the moment, obtained an effective version of the p-curvature conjecture for first-order differential equations with rational coefficients. However, the Chelmsky proved a much more general case of the conjecture, which is first-order equations with algebraic coefficients. So we would like to obtain the same kind of statements that that I presented to you for this kind of equations. And more generally, we are interested in effective versions of all proved case of the p-curvature conjecture. And last, we would like to link also more precisely our problem with the problem that I presented to you of the smallest prime that does not split, because for the moment, as the parameters are different, we cannot really state our theorem we cannot really compare our theorem to the known theorem in this field. And thank you for your attention.
Okay. Okay, thanks, Lucas. Lucas?
Okay, so
Yes.
please, can you go back to slide 16, I think?
Yes.
Yeah. Okay, so in this case, what exactly is the difference between the first case and the second and third cases that makes sigma be so much larger?
Good question. I actually do not know. Yes, I probably know. So it's probably the height of the coefficients. So if you see on the last case, we only have very small coefficients, -1, 1, and 2. Whereas in the second case, we have this 6 and this 4. So if you take Rothstein-Traeger's resultant, we will multiply this coefficient. So I believe that this is the reason our sigma is larger in the second case than in the third case.
Oh, okay, so like what the thing that makes sigma get larger is the size of the coefficients of the polynomials. Is that right?
Yes, partly, yes.
Oh, okay, I see. And just out of curiosity, so how much time did it take to run these second and third examples? I mean, is it a matter of seconds, minutes, or days? I don't know. Yeah.
Yeah, it's a matter of minutes.
Okay.
The second example ran in 30 minutes, and the last one also. But the last one, it's when we computed all the p-curvatures, whereas we only need to stop at the 5 curvature.
Yeah.
But as I said, also the algorithm we use is not optimized, and we can expect to have smaller bounds. Even I presented you values of m and n and sigma, but we can hope for a bit smaller bounds with the same method.
Yeah, perfect. And I mean, last question, like how many examples have you actually computed with this algorithm? Like, is it enough to, detect some patterns or some nice observations about, a way to predict if a certain rational function gives an algebraic solution or not? Like, are there some nice things to observe from the data?
We have not computed enough, I think, to conclude for the moment, or to have an idea, conjecture on what could be algebraic or not. But I believe that I don't know. I do not hope that I would see by the eye that a certain rational function gives an algebraic function because it's like I don't know. I do not hope for that, but maybe someone else can.
Yeah. So, okay, thank you. Yeah, go ahead.
Lucas, so your sigma is far from being effective, no? For example, this 5 curvature already, one example say that it might be too big.
What do you mean? Do you mean that we
you can say that maybe there is a smaller
you would
sigma.
want to have a sigma.
What I'm saying, there might be some smaller sigma satisfying.
Yes, we can hope for that.
Okay.
Yes, so we hope to. So with our method, we hope to have a lower bound on we hope to have some smaller sigma, but not. We don't know how lower can we go. We can go. However, as I said, as an observation in the beginning, really we indeed can hope, but with probably other methods, to have a much smaller sigma, because indeed here the 5 curvature already does not vanish, and so we can already conclude. So I think this is also the strength of this approach. It is whenever we have transcendental output, we can conclude very easily. The problem is when it is algebraic, we can certify that it is algebraic only with quite long computations.
Hi, Lucas. My question is, Lucas, the other Lucas here in IMPA mentioned for you that the difference here between the second case in this slide and the first case was partially by the coefficients. Like we have the 6s coefficient and 4s coefficient, and the sigma has turned much bigger. And my question is if there are other factors that, other things that make this sigma that bigger. Just in that cases that seems no, the 16 slide. Yeah, my question is why
yes, sorry, I was just going to this slide to answer.
All right, my question is why the sigma has grown up so much on the first case to the second. Thank you.
Yes, thank you for your question. So I think it is also related to the coefficients of the polynomials I and B on the one hand, but also on the second hand, you see that we have another other things going other parameters. So we have this B, but I think it's I think the main thing really comes from this delta. So this delta is the leading coefficient of the Stein-Prager resultant, and it is equal to the resultant of B and B prime. And this is really what makes everything grow. Like it grows M by in a cubic way, and here also in the cubic because there's an M here. And so in the end, sigma is approximately delta to the 6. So sigma grows very quickly with delta. And if I come back here, you can see that here, if we compute the resultant of B and B prime, we will obtain something like, I don't remember, but something maybe like 3. And whereas here we will have 31, I think, or something like that. So 3 to the power 6 is not so much, is not that big, whereas 31 to the power 6 is already much bigger.
Right. Can you go back to the 13th slide, please?
To the which slide, sorry?
First thing. Third. 13? 13, yes, 13.
13.
Yes. Can you give me a little intuition why this number 2826 in the M definition?
Yes.
It could be a
yes,
little
so
intuition.
This number is actually not completely random. So this number is actually a constant coming from, so in the Chernovsky proof at some point, there is a statement that the least common multiple of the n first numbers, so the least common multiple of 1, 2, 3 up to n, can be bounded by some constant to the power n. This 2.826 is an upper bound on this constant, and the constant comes from it comes from study of Chebyshev, because the logarithm of the LCM of the n first integers is Chebyshev's function, and explicit bounds on this function has been given by Rosser and Schoenfeld, I think. And so we just took an approximation of this constant, but it seems random here indeed, but it is not. So it is a constant that has satisfied that to the power n it is greater than the n first, the LCM of the n first integers.
Perfect. The work of yours and first scene are already in the archive, I assume. Yes. Can I?
No, it is not yet. But
Okay.
Yes, I was interested.
We hope to publish an archive.
All right. Thank you for the answers.
Okay. If there is no question,
Thank you.
so let's thank Lucas and also Florian for joining us today. Okay. Thanks again.
Thanks.